Hi people, so this is the final video for this topic and it's on tangents and normals. Now there's lots of examples here and I'm actually not going to go through all of them, I'll just go through a couple. These are really good problem solving questions, so just have a go at the questions and try and think about the scenario and really problem solve it out rather than trying to follow a specific process all the time. But there are some fundamentals that we can go through. And the solutions to all the examples are given on the OneNote. So we know that a tangent is a straight line which touches a curve at a point. That's the fundamental definition of a tangent. Now a normal though is a straight line which cuts the curve at right angles. Another way we can say that is that it's perpendicular to the tangent at some point. So say we've got our tangent here, that's our tangent, then our normal would look somewhat like this. You'll notice that that's a right angle in there, and that's the normal. Now we call this in here the point of contact, and it also happens to be the point of intersection. Alright, so this is the point of contact or intersection. So in order to find the equation of a tangent or normal, which is the types of questions you'll be asked often, you'll need a point which you can find by substitution into y equals f of x. And you will also need its slope. And you find that, of course, by substitution, and that substitution into the derivative, y equals f dash of x. So let's do an example. Find the equation of the tangent to y equals 3x squared, take 4x plus 5 at the point where x equals 2. So firstly, we've got our point of contact. There are two pieces of information. Remember, we want the point of contact and we also want the slope. So our point of contact, we've already been told, it's the x is 2. If we go over here and work out the y value when x equals 2, we're just going to substitute in 2. So we'll get 3 by 2 squared, take 4 by 2 plus 5, and that gives us 9. So we're going to get 2 9. So that's our first bit of information. Then our slope of your tangent, well, we're going to use the derivative to do that, and we want to substitute into the derivative because we've got y there. I'm going to talk about dy dx as my derivative. So dy dx is going to equal 3 over 6x take 4, so we're going to multiply down, subtract 1. 2 times 3 is 6, so 6x take 4. And then we're going to find that slope at that specific point. So we're going to find dy dx when x equals 2. So that's going to equal 6 times 2 take 4, which is equal to 8. So that's our specific derivative. Now, just remember you can write that as positive 8 over 1. That's going to help with normal questions. So therefore, the equation of the tangent is just going to be, we're going to do this using the slope formula. Remember the slope formula is y2 take y1 over x2 take x1. That equals the slope. So I'm going to go to slope 8 is equal to, then instead of putting y2 and y and x2, I'm just going to put in general y and x. You'll see why in a minute. I'm going to put y take, and then I'm going to use this point up here. So it's going to be y take 9, which is the y value, or y1, over x take 2. Alright? Now I'm not quite in the right format yet, but if I cross multiply, that means I'm going to get 8 bracket x take 2 equals y take 9. So 8x take 16 equals y take 9. So y equals 8x take 7. Now I'm just going to add in an extra bit here, finding the equation of the normal. The reason I'm doing that is just so that you don't have to go through a whole other example. When we went up here, we said the slope of the tangent was 8. That means, remember, that the slope of the normal is going to be the negative reciprocal. So the slope of the normal, we're just going to flip it and change the sign. So our slope of our normal then would be, if we flip 8 over 1, it's going to equal negative 1 over 8. All right, then we do therefore the equation of the normal. And again, we use the slope formula up, as you can see up there. So we're going to use this. We're going to go m, or the slope, -1/8, equals, and then instead of y, we're going to 2 and y1, we're just going to write y and x. Y take, well, what value? Well, it's still the same point of contact, isn't it? If you look back up here, if we look back up here to our picture up here, the normal still has the same point of contact as the tangent. Alright, so we can still use the point of contact 2, 9. So it's still going to be y take 2 over x take 9. But when we cross multiply, that of course will give us a different value. So it's going to be -1 bracket x take 9. This is going to equal 8 outside of y take 2. I've just cross multiplied there. So negative x plus 9 is going to equal 8y take 16. So 8y then is going to equal -6 plus -x plus 25. 8y equals -x plus 25. You could then divide both sides by 8 and get y equals -x plus 25 over 8. So that's how we find the equation of the normal, and we find the equation of the tangent. Just remember, when we're talking about equations of normals, that we probably wouldn't talk about the point of contact, rather we'd talk about the point of intersection, because the normal actually cuts the graph. So I'm going to skip question 2 because it's very similar to what we did in question 1. Consider this function now in question 3, and it says find the equations of any horizontal tangents. Well, if it's got a horizontal tangent, that means something. Okay, so try and interpret what these words mean. Horizontal tangent means like that. So that means its slope equals 0. Therefore, f dash of x is going to equal 0 at that point. All right? So firstly, let's find, in general, the slope, because that's going to help us, the derivative function, because that's going to help us find the equation of the tangent. So if we go f dash of x of this function, that will equal, multiply down, subtract 1, 6x squared, take 6x, take 36. Now we're trying to find when the derivative of the slope is equal to 0. So f dash of x is going to equal 0 when 6x squared take 6x take 36 equals 0. And then we can factorize that, and we take out a common factor of 6, and we get x squared take x take 6 equal to 0. Now if you use sum and product to solve that, you'll get 6 outside of x take 3 times x plus 2 equals 0. And so therefore, if you use null factor law, f dash of x equals 0 when x equals 3 or x equals -2. Because by null factor law, one of these must be equal to 0 for that equation to equal 0. Okay, so then we've got the slope. We've got we don't have the slope, we have the general equation of the derivative. We've now got these 2 points, so let's get our points of contact. Remember, that's what we need. So we need our points of contact. So the 2 points of contact are, and you can just substitute that in to the equation for f of x, and you will get, when you do that, I'm not going to show the working out here, but you just show your working out for substitution, you would get 2 points, -2 and 49, and you would get 3 and -76. Now, equation to the horizontal tangent. Well, if the point of contact of that tangent is right there at this point, a horizontal tangent, if you think about a Cartesian plane, is only going to have a y value. So the points of contact, the y value of the point of contact, is actually going to be the equation of the tangent. So therefore, the equations are y equals 49 and y equals -76. Alrighty, showing that the curve has no horizontal tangents. Well, if it's got no horizontal tangents, that would mean that for some reason the derivative is undefined, and that could be either a over 0 or 0 over 0. It doesn't work for either of those. So let's first do our thing. We can't really find the point of contact here, so we're just going to find straight to the derivative. So instead of writing it as a third, I'm going to write it as an indices. So I'm going to write 5x to the half, take 2. So therefore dy on dx is going to equal 5 on 2, x to the negative a half. And that is going to equal 5 on 2 root x. Now, dy on dx is not equal to 0 for all x greater than 0. The reason why that is because a fraction is only equal to 0 when the number on the top equals 0, right? So when the numerator equals 0, and the numerator obviously doesn't equal 0 here, it equals 5. So that is why this derivative can't equal to 0. This just means for all. That's what that sign means. So therefore, y equals 5 root x take 2 has no horizontal tangents. Now, part B of this says to find the equation of the normal. So you're going to do that the same way as before. You're going to find the point of intersection. I'm not going to write it out. I want you to have a go at it. You're going to find the point of intersection, and then you're going to find the slope, because you will have found the derivative. So you do the slope of the tangent, which will give you, and then you just have to negative reciprocate that to be able to get the slope of the normal, and then you write the equation, etc, etc, etc. So I'm not going to go through that any further than that. This is another lovely question. The tangent to this chord, to this curve where a and b in constants is 10x take y take 4 at the point where x equals -1, and find the values of a and b. So with this, you've got some unknown values and you've got some known values. So start with the known and then work with the unknown. Okay? So start with the known, and remember you're trying to do two things. You're trying to get the point of contact, and you're trying to get the slope. Okay, so that's the known. If we wrote that in slope-intercept form, we would actually get, if we rearrange that, we would get -y equals -4 take 10x, so y equals 4 plus 10x. Alright, now that's telling us a piece of information. We've got, we can get the point of contact first. So point of contact. So that's suddenly all filled out. But what we're basically doing here is we're doing exactly the same thing. So we're starting with the unknown, we're going to work with the known. And then we're starting with the known, and then we're going to work with the unknown. We're first going to find the point of contact and the slope of the tangent with the known facts. Then we'll find the point of the contact and slope of the tangent with the unknown. So from the equation of the tangent, for the point of contact, we know that x equals -1. So if we substitute that in, we'd get 10 times -1 take y is going to equal -4. So -y would equal -4 plus 10. It's going to give us 6. So y is going to equal -6. So our point of contact, therefore, is -1, -6. Now our slope of the tangent, if we just look at here and think about slope-intercept form, the slope, of course, is the number in front of the x. So our slope is just going to be equal to 10. Okay, now from the equation of the curve, let's find the point of contact. Well, we've got f of x equals x squared times 3x squared, x squared times 3x squared plus x plus b. To find the point of contact, all we're going to do is substitute in where x equals -1. So over here, I'm just going to write that. So I would do this, f of -1 is going to equal -1 all squared. If we substitute in -1 for x, we're going to get 3 take a plus b. That's a take right there. So 3 take a plus b. So that tells us that our point of contact is actually going to be -1, comma, 3 take a plus b. Beautiful. Now the slope of our tangent, well, that's a little bit harder, but to do that we actually need to be able to find the derivative. So to first do that, I'm just going to expand f of x. I'm going to expand through that x squared term, if you have a look at it, and you'll get 3x to the 4 plus ax to the 3 plus bx squared. So f dash of x then, if we find the derivative, is going to be 12x cubed plus 3ax squared plus 2bx. So therefore f dash of -1, we're going to substitute in -1, and we're going to get 12 dash of, to actually find the slope, -1 squared plus 3a times -1 squared plus 2b times -1. 12 by -1 cubed, sorry. So that gives you -12 plus 3a take 2b. Now we have all these things now that are equal to each other. We've got the slope of the tangent here, and we've got the slope of the tangent here, and we've got a point of contact here, and up the top we've got our point of contact right here. So what we can do now is just equate all those bits of information. Alright, so if we equate these facts, it gives the following, which looks like that. Looks like that. So what I'm just going to do is call that 1 and call that 2, and I'm going to solve these simultaneously. So I'm going to multiply equation 1 by 2, because that will put a number 2 in front of this b, so I can add the equations together and eliminate. So I'm going to make that 6 take 2a plus 2b equals -12, and I'm going to call that 1 dash, and then I'm going to do 1 dash plus 2, and I'm going to add those two equations together now. So I'm adding this equation with this equation. If you write them underneath each other, it's probably easier to see what happens. So if I add those two equations together, on the right hand side, I'm going to get 10 plus -12, which is -2. If I add 2b and -2b, they're going to cancel out. So I'm going to add 3a and -2a now. That's just going to give me a. And then I'm going to do 3 plus -12, and that's going to give me -6. So I get -6 plus a equals -2. Alright, and so therefore a is going to equal 4, and then if we go sub into 1, into equation 1 up here, we're going to get b. So 3 take 4 plus b would equal -6, so b equals -5, and so therefore we've done what we want to find, found what we want to find, therefore a equals 4, b equals -5. Now that's a relatively long question, as you can see, but remember all we've done is we've found the point of contact and we found the slope of the tangent, found the point of contact, found the slope of the tangent, then we equated it. Because we had the equation of the tangent, we were able to find exact points, an exact slope, and exact point of contact, which therefore enabled us to equate it. So they're not really that difficult if you remember to do finding the point of contact and finding the equation of the tangent. So I'm not going to go through any more. If you want some more examples, the notes for these are all up, but what I'd really suggest you do is to start doing some. Practice makes perfect.